Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
James Clerk Maxwell, a towering figure in 19th century physics, perhaps best known for his unification of electricity and magnetism, also made significant, if less celebrated, contributions to the theory of control systems. His 1868 paper, formally published as on Governors in 1869 within the Proceedings of the Royal Society of London, represents a pivotal moment in the development of cybernetics and control engineering. This work moved beyond purely empirical observations of mechanical governors to a rigorous mathematical analysis, laying the foundation for understanding stability in feedback control systems, a concept crucial to many aspects of modern engineering and automation. The intellectual genesis of Maxwell's interest in governors can be traced back to the burgeoning Industrial Revolution. Steam engines, with their inherent need for speed regulation, were ubiquitous, powering factories, trains and ships. The centrifugal governor, invented by James Watt, was a common mechanism for maintaining a desired engine speed. This device, consisting of two weighted arms that rise and fall with changes in rotational speed, adjusts a valve controlling steam flow to the engine. As engine speed increases, the arms rise, reducing steam supply and slowing the engine. Conversely, a decrease in speed causes the arms to fall, increasing steam supply and accelerating the engine. While Watt's governor proved practically useful, its behavior was often unpredictable. Engineers observed instances of instability, where the governor would cause the engine speed to oscillate wildly, rather than settling at the desired value. There was a clear imperative for a deeper theoretical understanding of these phenomena. Prior to Maxwell's work, the analysis of governors was largely empirical. Relying on trial and error and intuitive adjustments, engineers lacked a systematic method for predicting stability or optimizing governor design. George Biddle Airy, the Astronomer Royal, had studied the problem in the context of controlling the speed of telescopes but relied on approximations that were not always accurate. What was missing was a comprehensive mathematical framework capable of capturing the dynamic behavior of the governor and predicting its stability under varying operating conditions. Maxwell's paper addressed precisely this deficiency. On governors, Maxwell formulated a set of differential equations describing the motion of the governor and the engine it controlled. He made several simplifying assumptions for tractability, such as linearizing the system dynamics around an equilibrium point. This meant approximating nonlinear relationships with linear ones, a common technique in control systems analysis when deviations from a desired operating point are modest. The core of his analysis involved expressing the system's behavior in terms of a characteristic equation, a polynomial equation, whose roots determine the stability of the system. Specifically, he showed that if any of the roots of the characteristic equation had a positive real part, the system would be unstable, leading to oscillations or even runaway behavior. This criterion, while presented in a specific context, represents a fundamentally important result with broad applicability. Maxwell did not provide a general method for solving for stability. That achievement is attributed to Edward John Routh. Maxwell posed the problem while Routh solved it mathematically. The Routh-Hurwitz stability criterion states that the characteristic equation's coefficients determine the system's stability. The stability criterion allows engineers to assess stability from the coefficients of a polynomial without explicitly calculating the roots. This proved remarkably practical, allowing for analysis and design improvements without cumbersome root finding. The immediate impact of Maxwell's on governors was considerable. While it did not instantly revolutionize governor design, it provided engineers with a new theoretical foundation for understanding the behavior of these crucial devices. The paper's rigorous mathematical approach established a precedent for the analysis of feedback control systems, shifting the field from empirical observation to predictive modeling. It spurred further research into stability criteria and control system design, laying the groundwork for the development of more sophisticated control techniques. The legacy of Maxwell's work extends far beyond the specific context of steam engine governors. His analysis of stability, cast in terms of characteristic equations and root locations, became a cornerstone of control theory. His principles found application across diverse engineering disciplines, including electrical engineering, aerospace engineering, and chemical engineering. The concepts of feedback, stability, and system response, elucidated in his paper, are fundamental to the design and analysis of countless control systems used today, from autopilot systems in aircraft to process control systems in chemical plants. Subsequent research has significantly expanded upon Maxwell's initial work. As mentioned, Routh provided a practical algorithm for determining stability. Later, Adolf Hurwitz independently developed a similar criterion, leading to the Routh-Hurwitz stability criterion, a standard tool in control system design. Other researchers developed methods for analyzing nonlinear systems, which Maxwell's linearization approach did not address. These methods include describing function analysis and Lyapunov stability theory, which provide powerful tools for understanding the behavior of complex control systems. A subtle aspect of Maxwell's contribution lies in its connection to the development of cybernetics, a field that explores the principles of control and communication in both living organisms and machines. Norbert Wiener, a key figure in the development of cybernetics, explicitly acknowledged the influence of Maxwell's work on his own thinking. Wiener recognized that the principles of feedback and control, so clearly articulated in Maxwell's analysis of governors, are fundamental to understanding the behavior of a wide range of systems, from physiological regulation in the human body to social and economic systems. Maxwell's on governors can thus be viewed as an early precursor to the broader field of cybernetics, highlighting the unifying principles that govern the behavior of interconnected systems. The reception of Maxwell's paper was initially mixed. Some engineers, steeped in empirical tradition, viewed the mathematical analysis with skepticism, preferring to rely on their practical experience. Others, however, recognized the value of Maxwell's theoretical framework and embraced the opportunity to apply mathematical tools to control system design. Over time, as the power and generality of Maxwell's approach became increasingly evident, it gained widespread acceptance within the engineering community. The influences on Maxwell's work were multifaceted. He possessed a deep understanding of both mathematics and physics, allowing him to bring a unique perspective to the problem of governor stability. His familiarity with the work of mathematicians such as George Green and William Rowan Hamilton, who had developed powerful mathematical techniques for analyzing physical systems, undoubtedly shaped his approach. Maxwell was also influenced by the practical concerns of engineers working to improve the performance of steam engines, motivating him to address a real-world problem with rigorous mathematical tools. The influence of Maxwell's on governors on others is undeniable. Routh's stability criterion, directly inspired by Maxwell's work, became an indispensable tool for control system engineers. The concepts of feedback and stability, central to Maxwell's analysis, permeated the field of control theory, shaping the development of new control techniques and applications. Wiener's cybernetics, with its emphasis on feedback and control in diverse systems, can be seen as a broader extension of the principles articulated in Maxwell's paper. Maxwell's work continues to inspire researchers in control theory and cybernetics, a testament to its enduring significance. In retrospect, On Governors represents a remarkably prescient contribution to the field of control systems. It demonstrated the power of mathematical analysis to understand and predict the behavior of complex systems. The principles of feedback and stability, elucidated in Maxwell's paper, remain fundamental to the design and analysis of control systems today. While Maxwell himself may have viewed his work on governors as a minor diversion from his more celebrated contributions to electromagnetism, it stands as a testament to his intellectual breadth and his ability to apply rigorous mathematical tools to solve practical engineering problems. His work laid the foundations for a field that continues to shape our technological world, a subtle yet profound impact of a mind that truly understood the underlying principles governing the universe. Consider the simple example of cruise control in a modern automobile. The system maintains a constant speed despite variations in road grade or wind resistance. This is achieved through a feedback loop. The car's speed is continuously monitored by a sensor. This actual speed is compared to the desired speed set by the driver. Any difference between the two, known as the error signal, is fed into a controller. The controller adjusts the engine's throttle to reduce the error, increasing the throttle if the car is too slow and decreasing it if the car is too fast. The stability of this system is paramount. If the controller is poorly designed, the system could oscillate, causing the car to speed up and slow down repeatedly. Maxwell's analysis provides the theoretical framework for designing a stable cruise control system, ensuring a smooth and comfortable ride. Another compelling example arises in the field of robotics. Robots performing precise tasks, such as those on assembly lines, depend on sophisticated control systems. These systems must accurately control the robot's movements, compensating for external disturbances and ensuring stability. Consider a robot arm welding two pieces of metal together. The arm must move along a precise trajectory, maintaining a constant speed and orientation. The control system uses feedback from sensors to monitor the arm's position and velocity. This information is compared to the desired trajectory, and the controller adjusts the motors driving the arm to minimize any errors. Again, stability is crucial. An unstable control system could cause the robot arm to shake or vibrate, compromising the quality of the world. Maxwell's principles provide the theoretical basis for designing stable and accurate robot control systems, even in biological systems. The principles elucidated by Maxwell find resonance. The human body, for instance, employs numerous feedback control mechanisms to maintain homeostasis. Body temperature regulation serves as a prime illustration. When body temperature rises, sensors in the skin and brain detect the change. This information triggers a series of responses, including sweating and vasodilation, which help to dissipate heat and cool the body. Conversely, when body temperature falls, shivering and vasoconstriction are initiated to generate and conserve heat. These feedback loops ensure that body temperature remains within a narrow range, essential for proper physiological function. While the biological mechanisms are far more complex than a simple mechanical governor, the underlying principles of feedback and control are strikingly similar. It is perhaps a testament to the elegance and generality of Maxwell's approach that it has found application in such diverse fields, from the mundane task of maintaining a constant speed in an automobile to the intricate control of a robotic arm and the complex regulation of body temperature. The principles he articulated in On Governors continue to resonate, shaping our understanding and control of the world around us. It showcases exceptional insight, linking seemingly disparate systems through the unifying lens of feedback and stability.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.